Thanks very much, Giovanni, again. And it's a pleasure to participate in this workshop. I was participating in several of them actually, and it's always interesting to do so. So my title of my talk today is rather general. It's about far infrared light, driving magnetization, dynamics, and switching, but I will concentrate on phonon resonances. So this is what will be the subject, how we can switch magnetization using phonons in this case. And before I start, I would like to thank first all people that were actually doing the work. In particular, first of all, my group in Nijmegen at the Free Electron Laser Felix, and then other colleagues from Nijmegen, Delft, Bialystok, and Stuttgart, and various money-giving agencies. So if we're speaking about switching of magnetization nowadays, I should say there are many recipes already how you can do it, all optically, just using laser pulses. So for example, the first discovered was, well, I shouldn't say simple, but purely thermally induced switching. If you just hit a ferromagnetic metal quickly with a laser pulse, then several of them just switch magnetization to opposite. And this is a toggle switching, so every next pulse just switches magnetization and again. And it was first observed in that classical material as a gadolinium iron cobalt alloy, but then it was recently shown in terbium cobalt multilayers, and also in this Hössler alloy manganese ruthenium gallium. Then in ferromagnetic multilayers, it has been shown that if you have patience and use not a single pulse, but many of them, then you can switch magnetization into direction which is purely defined by the helicity of the laser pulse. So that has been shown first in the science of 2014, but then also several materials were shown to reveal this kind of magnetization switching. Maybe more interesting from several points of view is when you can switch magnetization without relying on temperature increase of your sample. Thus, we have recently shown that you can do so-called cold switching. You can generate extra magnetic anisotropy of your sample, which is strong enough to switch the magnetization. So this effect is purely non-thermal. The temperature increase of the sample during this effect is actually negligible. So the question is, can we find another non-thermal approach to switch magnetization? Well, it has been proposed a while ago, and here for introduction, a couple of steps in this direction. First, it has been shown that picosecond pulses of acoustic of strain, basically propagating through the substrate into the magnetic film, were able to trigger magnetization precession that happened clearly because these strain pulses were affecting magnetic anisotropy. So this is a very clear example of the magnetic precession driven by the strain pulses. And it was, of course, suggested that the same strain pulses can be used to switch magnetization. So this concept was developed a few years later, and you see that depending on the pulse widths and well, strength of the pulse, you can have several regions where switching will be possible. So let's see how we can apply this in reality. In reality, if you want to apply something strong, you can actually use a phenomenon of resonance. And it's very well known that resonant excitation, let it be even in low amplitude, can have really drastic effects, like it happens with this bridge. It's just wind that creates this effect. And it's also very well known what was the end of this bridge. It collapsed completely. So we don't want collapse, but we can ask a question whether such resonant excitation can be used for a useful and a constructive effect. Yeah. Now we have to think what kind of excitation we want to create in our sample to have switching. We need some change of magnetic anisotropy, strain-induced change of magnetic anisotropy probably. That is not rapidly oscillating. Yeah. Well, for this, we need some coupled oscillators and nonlinear phononics. I would like to show you this example, which is more than 100 years old, actually, and this is a pendulum, which consists of a solid stick and a mass. And normally, you know that pendulum has a stability position downwards. But if you start oscillate its point of suspension in vertical direction very rapidly, then first another stability direction appears, and this is just upside down. Very strange behavior for a pendulum. Moreover, if the amplitude is strong enough, then stability direction down will disappear. It will be only stable in upside down direction. Translated to the phonons in solids, it has been shown that if you can excite an infrared active mode to large amplitude, then a coupled orthogonal Raman active mode will show a shift in its equilibrium state. Yeah. So this is not creating a completely new equilibrium, but nevertheless shifting equilibrium to a side. Was taken into account in many materials, and it has been calculated. For example, in this praseodymium manganate, you have a shift of equilibrium position. In lanthanum cuprate, you have actually, similar to Kapitsa's pendulum, you have formation of a new equilibrium state in this. So how we can apply this? Well, first we need a sample, and this is something very similar to what Sergei just shown. It's again YIG, but in this case, some cobalt was added there mostly to modify magnetic anisotropy. Yeah. It's not only modifying anisotropy, but also increasing damping a lot. It's nothing compared to pure YIG, in fact. Nevertheless, the anisotropy in it is a cube, and a cube with an easy axis along diagonals. So in fact, it would have 8 easy directions of the magnetization. And spectra, optical and infrared spectra of the garnets are very well known. You have different types of transition invisible, but what we are interested in are these optical phonons that are really unbelievable. Something happened. So, can we use these phonons to switch? Well, we need a source of excitation, and this is the laboratory where I'm working. Now, this is our building, and somewhere in the basement of this building, we have a free electron laser, actually more than one, a set of free electron lasers that in total gives us radiation tunable between, well, less than 3 micrometer and almost 1.5 millimeter. And the energy, typical energy in our interesting range is several tenths of microjoule per pulse, which can be sub-picosecond long. Well, the free electron lasers have sometimes, well, they all often have this weird time structure. So the radiation comes in so-called macro pulses at a frequency of 10 Hertz. And inside the macro pulse, there are so-called micro pulses that can be really sub-picosecond short, but they follow at rather high repetition rate. So for the purposes of our experiment, we just used a very simple setup made of a silicon plate, which is transparent for the infrared, but if you illuminate it with a pulse of YAG laser, it becomes a transient mirror, and you just extract a single picosecond pulse. Just to tell you, we did some more work on this, and we managed to extract a single pulse from inside the laser cavity. So that increased our available pulse energy up to a couple of hundred of microjoules in maximum. So let's apply these pulses and see whether we can switch anything. So this is the main structure. We put a sample in a polarized microscope. We saturated all of it in this diagonal direction. And this circle roughly shows you irradiation spot, which is, of course, having a Gaussian profile. So single micropulse at 14 microns, and then you see this domain pattern appeared. So from one saturated, from the sample saturated at one direction, we now created 4 domains that have these directions of magnetization given by these arrows. First, we try to set the initial condition of a sample different, just setting the magnetization along different axes. And you see that pattern sort of rotates together with pattern sort of rotates together with the magnetization. If you direct it opposite to each other, then domains change contrast. But if you rotate 90 degrees, then this pattern also rotates 90 degrees. So this is one thing that should be noticed. And second thing which should be noticed, in fact, at the center of the beam, there is nothing. Yeah. So here the intensity was maximum, nothing is created there, only on the sides, and also only in the direction perpendicular to magnetization. And then another weird thing was that you can apply one pulse, it will reverse, and then you apply 10 other pulses, it will stay the same, or hundreds of pulses, it stays the same. So in fact, this pulse slicing was not even necessary. You can use the full macro pulse. The effect is the same as from one single picosecond pulse. That's also something. So to prove that nothing really happens in the center, here is the profile. This is half of the Gaussian beam, and this is the switched area where you see this domain contrast. Nothing in the center of the beam, but really where you have the slope, where the intensity is changing. Then if you change the full intensity of the pulses, then you see that at some moment domains appear, and basically area of the domains becomes larger with the pump fluence. So what is there in the material that we excite with our laser? To answer this question, we measured phonon spectra just to be sure where they are and what kind of phonons we have. So we have peaks in absorption defining for us transverse optical modes, and you have peaks in this inverse epsilon, or in the optical loss function, what is properly called, that gives us longitudinal phonons. And what we found is that the switching, given here the efficiency of switching is given here by blue points, really repeats the pattern of longitudinal optical phonons. Nothing happens at transverse phonon, although of course at the transverse phonon, which is infrared active, absorption is enormous. You have very strong absorption effect there, but there is no effect there of domain switching. What kind of effect you can observe on the transverse phonon? Well, first, if you increase the fluence, you create this sort of demagnetized pattern, very small domains, probably because of the residual heating of the sample by the strongly absorbed. If you go further, you get this damage. Yeah, so this is these strong strains on the surface of the film, they just crack it. And what is interesting is that the cracks are along crystallographic axis. If we had 111 film, then it was really triangular pattern of these cracks. So this is something. Well, to understand a little bit dynamics of the process, what we could not do ourselves at Felix, we went to our colleagues in Delft, and they used optical parametric amplifier, the time resolve setup. However, they had lower pulse energy, so the switching was not observed, but you observe some magnetization dynamics precession in this, and you find that excitation efficiency again is maximum at the same wavelengths of the longitudinal optical phonon. So here the mechanism is somehow confused. So where does it come from? Why longitudinal? Well, I should say we are still working on it, but one thing that I can tell you is that in garnet films, because of the growth-induced anisotropy, the original inversion symmetry of the cubic crystal is broken in the direction perpendicular to the film plane. And so this direction is where atomic vibrations happen when we excite longitudinal phonon. They can be strongly anharmonic. And because of this, phonon-phonon interaction will be much stronger when we excite this. However, I should say that we are still working on this. Then, how to describe the pattern of these four domains? We did some calculation here, starting from, well, if you want to start somewhere, start from classics. Apparently, the problem of the radially symmetric strains has been already solved in the classical books of Landau and Lifshitz. You just take the results from there and integrate it for the Gaussian profile. From this, you calculate from the displacements, you calculate induced strains. And from this, you get a magnetoelastic energy that has a symmetric term that in fact will not change much in the sample. And you get this sort of anti-symmetric term. You put it into the micromagnetic simulations. You simulate time dependence of your pulse also by a Gaussian profile. And then you just shoot it, and that profile you get. So this is not exactly what we get, but in fact, in this simulation, we even neglected demagnetizing field. You just get these results purely from the strain-induced anisotropy modification. Then what about multiple pulses? Now we observe the same switching and again when multiple pulses are there. And here I just show you what happens. So this is first shot, domains are formed, and this is second shot. Maybe they increased a little bit, but they still are the same. And then you can just repeat these shots more and more, and they will basically stay there. So this is kind of switching you obtain, and in fact it shows you that standard pump probe setup that you can use for switching to try to observe the switching is rather useless in this case. Nothing happens here at the center of the beam where you typically try to observe with your probe pulse. Then the question is such a sample unique for this switching? It has cobalt contain which guides anisotropy and which gives you this this cubic form and gives you strong damping that allows quick formation of these domains. Well, we tried recently some other samples, and one example I want to show you. This is bismuth containing garnet. Domains are easy to observe. The contrast is huge. It's anisotropy is very weak in this sample. It's very soft magnetic film, and these are three different orientations of the same sample with respect to the magnetic field, which is applied here horizontally on this pattern. And you see it's after a single shot in every time of a laser at the phonon frequency, you get this domain pattern. But of course, it's much more interesting to see how this domain pattern is formed. For this sample, we kind of solved this problem, but also maybe not entirely. We have, for the imaging, a YAG laser with 5 nanosecond pulses. So this is what defines our time resolution in this case. And so we see that part of the pattern appears basically at overlap of our probe pulse and pump pulse. So very fast there. However, after that, you see very strange formation. You see formation of striped domains that propagate from the center of excitation And finally, they form this, at the end, this 4-domain pattern. So what happens here? You know or think that it has been observed many times that if you excite your magnetic sample locally, you have spin waves, spin waves that are magnetostatic, or you can have spin waves that are coupled with elastic excitation, magnetoelastic wave in this case, that propagate from the center. So here, our excitation is so strong that we see domains formed by these waves that propagate from the center. So we are still analyzing this. This is a very fresh result, and in fact, I believe from the velocity of propagating, how fast they propagate and how they behave, we might be able to make conclusion where these are purely magnetostatic waves, or maybe these are coupled magnetoelastic waves in this case. Okay. Before the end, one more thing that we observed with phonons again, but the observation comes from completely different corner. Now I come back to my very first picture in my presentation, to very first statement, but I just take this switching in gadolinium iron cobalt as it was originally observed, which happened to be rather confusing to interpret. At this experiment, we took circularly polarized laser beam and we scanned across the sample. And it has been shown that, well, one helicity gives you one contrast and another helicity gives you another contrast. This helicity dependence was a little bit of an artifact of circular magnetic dichroism in these films, while the real mechanism was, of course, toggle switching with a single shot. But you can try to do this at longer wavelengths. For example, you go to the same wavelengths in mid and far infrared, and then you see that at some of the wavelengths you have rather decent switching in one direction, at another wavelength you have nothing at all, and then this switching is again much better visible. Yeah, so what happens there? Well, here is the spectral dependence of this switching in blue points and optical phonons transfers in this case in the substrate, not in the sample, but it's fused silica substrate. It has very well defined phonons there, and you see that peaks of the switching is exactly at the phonon frequency. Moreover, strange point here is that because of this strong absorption in the substrate, you have even less intensity of your incident radiation inside gadolinium iron cobalt film. This is very easy to estimate. So what happens here? Well, theoretical answer, and to some extent has been given already. Recent times, people considered quite a bit these phonomagnetic analogs to optomagnetic effects. I believe many of you have heard of inverse Faraday effect, when circularly polarized light generates effective magnetic field there. If you excite a circular phonon with this light, that also produces effective magnetic field, and in some cases these fields were calculated much stronger, to be much stronger than electronic ones, because of the ionic motion. It can be more effective. That still needs to be confirmed, mostly experimentally, but I believe that what we observe is the fingerprint of such an effect. So to conclude, well, we did discover phonon-induced switching of magnetization. You have domain pattern that really proves that well, these radial strains are producing these, and the spectral dependence indicates the longitudinal phonons as a source. We think we understand it. However, we still need to do some more in this direction. Thank you very much for your attention.